In the next few examples, I would like to take you through just some other types of problems you maybe haven't seen yet, and just some other representations. So, like for example, the first thing I want to walk you through here is modeled probability. Now, what that means is instead of calculating it yourself and instead of trying to think of all the probabilities, they're just giving it to you. So they're telling you, here's a model we're going to work from. They're telling you the cardinality of the sample space is 10. They're telling you the cardinality of the event is 4. Therefore, can you find the probability? Well, yeah, the probability of our event would be 4 out of 10. And right, because it's the cardinality of the event divided by the cardinality of the sample space. So that would be 2/5, or that would be zero point 0.4, or that would be 40%, right? Just being silly, right? Any of the representations is fine. But the other thing I want to make sure I point out is the notation, right? Just make sure if you see a P with a little E in the parentheses, that's not multiplication, right? That's probability of the event. So this is where all of the set theory and the notation we were working on before, the sample spaces, um, number theory that we were learning before will come into play. Okay, so whoops, moving along, moving along. I scrolled a little too far. Here we go. So a little bit of modeled probability. Now you know that the probability of A intersect B is zero point 0.1. All right. So what does that mean, intersect? Well, if you remember, that means it's kind of like the concept of and. It's where they both have what they both have in common. So therefore, what we're saying is the probability of A and B occurring. So meaning both things have to happen. The probability of that happening is 10% or zero point 0.1. The probability of A just happening by itself is 70%. And the probability of B happening by itself is 30%. So therefore, the likelihood they want us to know, they want us to find what is the probability of A or B. All right, A or B. So I'm going to do this just to help us visualize our first one. I'm going to draw it using a Venn diagram. Say, okay, what's going on here? The probability of A happening we know is 70%. So that means everything inside this bubble has to add up to be 0.7. And I know the intersection is 0.1. So therefore, in here gets a 0.1, which means out here needs to get a 0.6. Stop and think about that for a second, because what we just said is the likelihood of A happening is 70%. So if you were thinking of it like a dartboard, you threw a dart at it, 70% of the time your dart's going to land inside this bubble. And what we've figured out is 60% of the time it's going to be in the A part, and 10% of the time it's going to be the A and B part, which makes a total of 70% of the time. And then, so similarly, the probability of B occurring, that happens 30% of the time. But again, 10% is already taken up here in the overlap. So that means out here we're going to have 20%. So because the 20% in B, but not in A, right, would add up with the other 10% to make a total of 30%. So I'm hoping the visual makes sense, and therefore you can logically say, well, then that means we're going to miss the bubbles. How often? Interesting. I know the problem didn't ask for it, but you can figure it out, right? Because we know the whole thing has to add up to 100. This is like a probability distribution table. I know I'm going to hit A 70% of the time. I'm going to hit B 30% of the time. I'm going to hit A and B 10% of the time. What am I going to miss completely, right? Well, if we add these up, we see 60, 70, 80, 90. So that means to make the other 100%, 10% of the time I'll be outside. Okay, now let's answer the question. They want to know what's the probability of being an A and B, um, or A or B, right? Both, either one. How often am I going to hit either one? Well, so if you look at it, this is 0.6. I know 60% of the time I'll be in A, then 10% of the time I'll be in A and B, and 20% of the time I'll be in just B, which means the likelihood of me hitting any of those things, A and B, would be, what did we just say, 90? 90%. So there you go. So this is the first part of the addition principle of probability. But what I will point out is there's another part to this. Whoops. Where if you just instead tried to do this, would it work? If you just try to do the probability of A plus the probability of B and not dealing with the overlap, you just took the numbers in here, you'd say, okay, well, that would be 70% plus 30%. So that means 100% of the time you're going to hit A and B. Well, no, that's not right, because we double counted the overlap, right? This overlap in the middle right here got counted twice. It got counted once when we counted A, and it got counted again when we counted up the B, when we did the probability of B. So what the addition principle says is, okay, you can do that. You can add A and B, but then, whoops, don't forget to subtract the overlap one time, because I counted the overlap with A, which is fine. I want to count the overlap, but only once. So since I counted it once with A and then I counted it once with B, I need to subtract the overlap one time. So then what that would give us, if you kind of look at it this way, it would be 0.7 plus 0.3 minus 0.1. So, which gives us 0.9. Hey, look at that. It's what we found before by just looking at the Venn diagram. So you have a way of doing this without actually drawing the Venn diagram, and that's using this formula. It's using the probability, the addition principle of probability. All right. Now, what I will point out is you don't have to memorize it, because you could just think of it. You can come up with it every single time you need to use it. Or memorize, your call. All right, it's not that hard to come up with though, right? You just draw little bubbles and say, oh, I'm counting this thing twice. All right, so now, this is just another little tweak to this idea. If I told you the probability of A intersect B is 0.7, the probability of A is 0.1, the probability is 0.3, let's do this, all right? So try it. Pause the video. Okay, welcome back. Let's see how you did. So the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. So therefore that results in, let's see, 0.1 plus 0.3 minus 0.7. Oh, interesting. So that's going to be, what, negative 0.3. Yay, put a box around it. We're done, right? What the heck? No, I'm kidding. But what does a negative probability mean? Right? What does it mean to have a negative probability? Well, if I told you the probability of something happening, if I told you the probability of an event was 0, what would that mean? It never happens. Ever. So what does a negative probability means? Like, we go back in history and anytime it may have happened then, take it away, it didn't happen? No, like, it happens less often than never? I don't know. So for probabilities, negative numbers don't make sense. So what that means is, I dare you, try to draw the Venn diagram of this. It's not possible. You can't have an overlap of 0.7 and have the whole thing only be 0.1, right? If this is A and this is B, how do I have an overlap here of 0.7 and then have the whole thing add up to make 0.1? What is this, a negative 0.6? That makes no sense. So this whole problem is nonsense, not possible. Not possible, right? So watch for goofy little things like having a probability that's negative, or what does it mean to have a probability of 1.4, for example? Well, again, 1 means 100%, which means it happens every single time. So when you throw one dart, it's going to magically split into 2, and then 40% of the time, that second dart's going to hit the... What? No, this doesn't make sense. You can't have 140% probabilities. Okay, so go away. All right. So I hope that helps. In the next video, we're going to talk about a couple other fun ideas.